Hello friends and welcome to this simulated tools available for logic gates based implementations tutorial. I am very excited to be your instructor and I will do my best to give you all the knowledge and the skills. First of all, let me introduce myself. I am Takshan. I am studying computer science and technology degree program at Uva Vellezha University, Sri Lanka. Okay, without any delay, let's move into the topic. First, let's see logic gate simulated tools. What is the Logic Gate Simulator? Logic Gate Simulator is an open source tool for experimenting with and learning about logic gates. Here you can see some example of Logic Gate Simulator tools. They are Logic Friday, Seda Logic Simulator, Deeds, Logism. But in this video, I am going to use Seda Logic Simulator. Okay, let's see Seda Logic Simulator and its installation. SIDA is an interactive digital logic simulator to be used for teaching of logic design or testing simple digital designs. It features both low-level logic gates as well as high-level components, including registers and SAT80 microprocessor emulator. Okay, let me share you a brief history about SIDA Logic Simulator. SIDA Logic Simulator was developed by Ben Sparak, Matthew Lane, and David Nearim for a senior design project for Cedar Village University during the 2005 to 2006 academic year. This name Cedar was taken from their university, Cedar Village. Fine. In my opinion, Cedar is a good logic simulator for beginners because it is simple to use program, has good response time, supports keyboard shortcuts, includes user documentations and runs on a moderate to high amount of CPU and system memory. We have not encountered any issue during our testing. Cedar Logic Simulator did not freeze, crash or pop up error dialogues. Fine. We can download it from sourceforge.net. If you come to sourceforge.net, you can able to see a web page like this. If you want to download it, you have to click this green color download button. And here you can see the last update. The last update is 26 to 2020. If you take a Logisim simulator, you have to download Java runtime environment. But in Cedar Logic Simulator, you don't need to download any environment or software. But it's only support for Windows operating system. If you are not Windows user, don't worry. Its latest release can be downloaded as cedarlscode.zip. It can be run online in the free hosting provider OnWorks for workstations. So you can download and run online this app named Cedar Logic Simulator with OnWorks for free. Okay, let's move. When you start the Cedar Logic Simulator, you will see a windows like this. This is our canvas, this is Explorer pane, and this is menu bar and this is toolbar. Okay, let's start the Cedar Logic Simulator. Okay, it is our Cedar Logic Simulator window. The interface of the program is plain and easy to work. From the left side of the window, you can insert object into the sheet by using drag and drop method. Okay, these items are mainly based on basic gates, inversions and connections, decorations, maxing and decoding, addition and comparisons, flip-flops, registers, RAM and ROMs, along with the chips. Fine. When you come into the invert and connect, you can able to see from gate and to gates. From or to gates are bidirectional junction between wires. Each to or from gate with the same name act like they are the same wire. Okay, the main application window includes 10 different pages. So you can work on multiple digital designs at the same time and seamlessly navigate back and forth between them. Fine. To save circuit, simply select Save from File menu. Okay. When you come into the Edit menu, you can choose Undo, Redo, Copy, Paste as well as export the project to monochrome or color bitmap file. On top of that, you may view an oscilloscope. It is used to show a timing diagram of your circuit. Fine. If you can't understand this stuff, don't worry. I am going to construct some circuits on Cedar Logic Simulator. After that, you can get a clear idea about Cedar Logic Simulator and you can able to construct circuit yourself by using Cedar Logic Simulator. Okay, let's move to the examples. I am going to take my first example from combinational logic circuit. Okay, let me tell you something about combinational circuit. This output is only dependent on present input. Combinational logic refers to circuits whose output is a function of the present value of the inputs only. As soon as inputs are changed, the information about the previous inputs is lost. That is, combinational logic circuits have no memory. The sequential circuit is just opposite to it. We will see it later. Okay. Here you can see some examples of combinational logic circuits. They are half adders, full adders, multiplexers, demultiplexers, encoders, and decoders. We can make a combinational circuit like this. This is our input and this is our outputs and this is our combinational circuit. The output is only dependent on these inputs. So let's move to one of the example in the combinational circuit and it is the half adder. Okay, half adder is a combinational logic circuit which is designed by connecting one XOR gate and one AND gate. The half adder circuit has two inputs A and B which add two input digits and generates a sum and a carry. It is used to add a single bit number. It does not take carry from previous sum. The output obtained from the XOR gate is the sum of the numbers, while that obtained by AND gate is the carry. There will be no forwarding of carry addition because there is no logic gate to process that. Thus, this is called half adder circuit. We can get sum is equal to A XOR B, carry is equal to A and B from this truth table. According this result, we can construct this half adder circuit. Okay, now let's try to build this half adder on Cedar Logic Simulator. Okay, the first thing we will do is to add one AND gate and an XOR gate. Now I am going to add an 2 input XOR gate. So place your cursor over the 2 input XOR gate in the gate palette so that a blue square appears around the gate shape like this. Okay, then hold the left mouse button down and drag the gate shape onto the gate canvas. Release the mouse button when the gate is at the desired location. Okay, then when you left click anywhere on the canvas, the gate will be unselected. Okay, like that I am going to add 2 input AND gate. So I click 2 input AND gate and drag and drop. Okay, fine. The next thing we will do is to add input and output. So I come to input and output. Here I am going to take on or off toggle switch as my input. So I click it, drag and drop. I want two input, so I take another toggle switch. Click, drag and drop. And I am going to take LED as my output. So click it, drag and drop. I want two output, so I am going to take another LED. Click, drag and drop. Fine. Next, I am going to make a connection between my switches and two gates. So I am going to select invert and connect. Then I click to gate, drag and drop. Okay. Uh, I have two inputs, so I take two gates. Okay. Now I am making to connection between from gate and my XOR gate and AND gate. So I select from gate. I want two from gate because I have two gates. So I select two from gate. Okay. Now you may ask me why we use this two gate and this from gates. As I already said, to or from gates are bidirectional junctions between wires. Each to or from gate with the same name act like they are the same wire. So we have to name it. To edit the connection of a to or from gate, simply double click on the gate and the dialog box will be appear. So I'm going to name it as A and click OK. So this is also A. Okay. I'm going to name it as B. So this is also B. Okay. Now it's time to connect wires. So place the mouse cursor over the output or input of one of the gates you are connecting until a red box, it's called hotspot, appears over the input or output. Left click on the hotspot, a green wire will appear when the hotspot is clicked on. While continuing to hold down the left mouse button, drag the wires towards the input or output of the appropriate gate. Continue to drag the wire until the hotspot of the output or input of the other gate appears. Release the left mouse button. The gates will now be connected by a wires. Okay, now we will connect all wires using this method. Click, drag, click and drag, click and drag. Okay, if you want to move anything, simply just click and drag and drop. Okay, now we make connection. Okay, fine. Now let's see about text. Here I'm going to give name to my outputs. So we have to go to decoration. Then select text object from the gate palette. After that, drag the text object to the appropriate position. Okay. Then double click on the text object so that the dialog box appears. Now you can give a name what you want. I'm going to give as sum. Then click OK. Like that, I'm going to give name to my other output. Okay, it is carry output. Okay, fine. Now let's check our half header. If both A and B are low, sum and carry are also low. If A or B is high, the sum will be high. If both A and B are high, the carry will be high. So our half adder is working correctly. Okay, let's move to our next example. I'm going to take my next example from sequential logic circuit. Hope you know about sequential logic circuit. Its output is dependent upon the present input, but also it depends upon the previous output. Here you can see some examples of sequential logic circuit. They are latch, flip-flop, counters, registers. Now I'm going to take latch from it. You already know about SR latch circuit using NOR gates. The bistable element is able to remember or store one bit of information. If the set input goes high for even a moment, the output goes high and stays high. Even after the set input returns to low, the output returns to low only when the reset input goes high. Okay, without further delay, let's try it on Cedar Logic Simulator. Okay, for constructing a ledge, the first thing we will do is to add two NOR gate. Okay, let's do it. I'm going to add two input NOR gate. So select NOR gate, click, drag and drop. Okay, I want two NOR gate. So select, drag, drop. Okay, the next thing we want to add inputs. So I go to input and output and I take on or off toggle switch as my input. Okay, I want to input, so I take two toggle switch. And also I am going to take LED as my output. I want two output, so I take two LED. Okay, fine. Now I am going to make connection between to and from gate and my inputs and outputs. So I take two gates and from gates. I want for two gates, so I take for two gates. Okay, like that I take four from gates. Select, drag, drop. Select, drag, drop. Okay, fine. Now I'm going to give name to my inputs and outputs. So double click. It is R. Select OK. It's S. Okay. Q. Okay. It's called Q bar. Q bar. Select OK. So this is also R. This is S. This is also Q. This is also Q bar. Okay. Now let's connect all by wire. So let's connect. Okay. Now let's check, does this SRLH works or not. If R is high, Q bar will be high. It's called reset. If both R and S are low, you can't see any changes. If both R and S are high, Q and Q bar will be low. If S is high, Q will be high. It's called set. So our SR latch is working correctly. Okay, now let's see the timing diagram of this circuit. So we have to go to view and select OSHO. Here we have to click none button and select our inputs and outputs. S, R, Q, Q bar. Okay, before check, I minimize my screen for a better view. Okay, now If you change the inputs, the timing diagram also change. You can see. Okay, just pause. Just see. uh, S low, R low, so no changes. uh, S high, R is low, so Q is high and Q bar is low. So our timing diagram is also correct. Fine. Let's move to our next example. Okay, I'm going to take frequency divider as my next example. You all know a frequency divider can be constructed from JK flip-flops by taking the output of one cell to the clock input of the next. The J and K inputs of each flip-flops are set to 1 to produce a toggle at each cycle of the clock input. For each toggle of the first cell, a toggle is produced in the second cell, so its output is at half the frequency of the first. Okay, let's try it on Cedar Logic Simulator. The first thing, we have to add JK flip-flops to construct the frequency divider. So let's do it. I want JK flip-flops, so I go to flip-flop, then select JK flip-flop, click, drag and drop. Here I am going to use 4 flip-flops to construct my frequency divider. So I take 4 JK flip-flops. Okay. The next thing, I'm going to add inputs. So I go to input and take toggle switch as my inputs. So I take 2 toggle switch. Okay. Next, I'm going to make connection between my toggle switches and my circuits by using 2 gates and from gates. So I go to invert and connect, then select 2 gates and from gates. I want 2 gates and from gates. Okay. Now I'm going to give name to my from gates. So my all inputs are J and K. So I give name it also J and K. J, K. Okay. But here I have 8 inputs. So I want 4 pairs of J and K gates. So I am going to copy and paste it so that you have to select it. Then you have to go to edit menu and click copy to copy these things. But simply we may use keyboard shortcut keys to copy it. So I press Ctrl plus C to copy it. Then I press Ctrl plus V to paste it. Okay. After that, you click your left mouse button onto a desired location. Okay. Like that. Ctrl plus V to paste it. Then clicked left mouse button. Likewise, Ctrl plus V to paste it. Then clicked left mouse button. Okay. Now I am going to give name to my 2 gates also. So this is also J and this is also K. Okay. Now I am going to make connection by using wires. So let's do it. Okay, fine. Here, we all know a frequency divider can be constructed from JK flip-flops by taking the output of one cell to the clock input of the next. So, we will do it. Okay, next we have to add our output. Here I am going to use two gates as my output. So I select two gates. I want four two gates because I have four outputs. Okay, now I am going to give name to my outputs. Okay, it's my first flip-flops outputs. So I give name it as output 1. So O1. Okay, then connect it. Fine. It's my second flip-flops output. So this called as O2. Okay, then connect it. Okay, this my third flip-flops output. So O3. Okay, then connect it. This my fourth flip-flops output. So O4. Then connect it. Okay, fine. Now I am going to add clock input by using to-gate and from-gate. So go to input and output, select clock input and go to invert and connect, select to-gate and select from-gate. Okay, now let's connect it. I add name as clock, CLK. So this is also clock. Okay. Okay. Now connect it. Okay. We all know in frequency divider J and K are always high. Now our frequency divider is ready. So let's check it by using timing diagram. So we have to go to view and select OSHO. Then we have to add our outputs, clock or O1, O2, O3, O4. Okay, let's pause it. Here, if we take this time as t, this is 2t, this is 4t, this is 8t, this is 16t. So, if we take its frequency as f, the output of the fourth cell's frequency is 1016f. So, our frequency divider is correct. Okay, let's move to the next example. I'm going to take my next example. First of all, let me tell you something about counters. You all know there are two main types of counters. They are asynchronous counters and synchronous counters. Okay. Here, I'm going to take BCD or decade counter to my examples. Okay. A decade counter is a binary counter that is designed to count to 1010. Okay. So, it's count 0 to 9. Here, I have taken a asynchronous counter because I don't give clock pulse simultaneously. Okay, let's build it on our serial logic simulator. Okay, first thing I'm going to add JK flip-flops. So I go to flip-flops. Then here I'm going to select JK flip-flop negative triggered because I want to count from 0 to 9. Okay, so select, drag, drop. I want 4 JK flip-flops. So we all know all JK inputs are high. So let's connect it by using from gates and to gates. So go to invert, select from gate and select to gates. Okay. I am going to select toggle switch as my input. Okay. Now let's connect all J and K inputs. Okay, let's do it. Okay. Now I'm going to give name to my inputs. So I add name as in. Okay. So this is also in and connected it with my toggle switch. Okay. Hope you all know the output of first flip flop will be the clock input of next flip flops. So it is a asynchronous counter. Okay, let's connect it all. Fine. Next, I'm going to add NAND gate. So I go to basic gates, and select two input NAND gate. Two input NAND gate. Okay. Select, drag, drop. Okay. Now its output is connect all clock, all clear. Okay. Let's do it. Now I'm going to give a name to my outputs by using two gates. So go to inverts and select two. Now I edit this name as uh, output 1. So O1, output 2. So O2. Okay, let's connect the outputs. We know for BCD counter, O4 and O2 are inputs of this NAND gate. So let's connect it. Finally, I'm going to give clock input to my circuit by using to and from gates. Okay, let's do it. Okay, now I edit name to my from gates and to gates as clock. CLK clock. Okay, this is also clock. Okay, now let's connect it. Okay, okay, let's on our toggle switch. Okay, now our BCD counter is working. Now I'm going to check it by using 4-bit LED display. So select 4-bit LED display and I want 4 from gates. So go to invert and connect and take 4 from gates. Now I'm going to name it as O1, This is O2. This is O3, and this is O4, because these are our outputs. Okay. Okay. Now let's connect it with our 4-bit LED display. This is O1, this is O2, this is O3. Okay. Awesome. Here you can see its count from 0 to 9. So our BCD counter is working correctly. Okay, let's move to the next example. Okay, encoders is my next example. We all know an encoder is a combinational circuit that performs the reverse operation of decoder. It has maximum of 2 n inputs lines and n outputs lines. It will produce a binary code equivalent to the input which is active high. Therefore, the encoder encodes 2 n inputs line with n bits. Okay. Here I have taken a 4 into 2 encoder and make this truth table. Uh, Q1 is equal to D2 plus D3, Q0 is equal to D1 plus D3. It is taken from this truth table. We can construct encoder like this. So let's construct it on our serial logic simulator. Here I want two OR gates to construct my encoder. So I go to basic gates and select two inputs OR gates. So I want two OR gates, so select two OR gates. Okay, fine. Now I'm going to add inputs. I'm going to add toggle switches as my inputs. So I select toggle switches. I want three toggle switches because I have three inputs in encoders. Okay. Then I'm going to add LED as my outputs. So I select two LEDs because I have two outputs in my encoders. Okay. Now I'm going to make connection by using two gates and from gates. So I go to invert and connect and select from gates and two gates. So I want three from gates to my inputs. So I want three to two gates to my inputs. So select 3. And also I want two gates to my outputs. Sorry. And also I want two from gates to my outputs. Okay, fine. Now I am going to make connection by using wires to construct the encoders. I am going to edit my inputs and outputs name. Okay, let's do it. I edit its name as D1. D1. Okay. I edit its name as D2 and edit its name as D3. Okay, so its name also D1, D1, its name D2. Okay, and its name D3. Okay, fine. Likewise, I edit my output's name also. I edit its name as Q0 and I edit its name as Q1. Q1. Fine. So it's also Q0, Q0, and it's Q1. Fine. Now let's make connection between uh, our switches and two gates. So let's make connection. Okay, let's check it. Does it works correct or not? Okay, when we will make D1 is high, the Q not is high and Q1 is low. So 1 0. Okay, when we will make D2 is high, our output Q0 is low and Q1 is high. So 0 1. Okay, when we will make Q3 is high, Q0 is high and Q1 is high. So 1 1. So our encoder is working correctly. Okay, let's move to the next example. We have just seen about encoders. Now we will see about decoders. Okay, and decoder is a combination circuit that performs the reverse operations of encoder. We will know a common type of decoder is the line decoder, which takes an n-digit binary numbers and decodes it into 2n data lines. Okay, here I have taken a 2 to 4 line decoder. This is the truth table of 2 to 4 line decoder, and we can make a circuit like this. Okay, let's build it in our serial logic simulator. Okay, first thing I'm going to add AND gate. So I go to basic gates and select two inputs AND gates. Here I'm going to build a 2 to 4 line decoder. So I want 4 AND gates. So I select 4 AND gates. Click, drag and drop. Okay, fine. Okay, now I am going to add inputs and outputs by using two gates and from gates. So I go to invert and connect and select from gates and two gates. I have two inputs, so I want two from gates, and I have four outputs, so I want four two gates. So okay, fine. Now I want two NOT gates to build this 2 to 4 line decoders. So I go to invert and connect and select small inverter as my NOT gate. Okay, I want two small inverter. Fine. Now let's build our decoder by using wires. Now I'm going to take toggle switches as my inputs. So go to inputs and outputs and take toggle switch. I want two toggle switch because I have two inputs. And I take two gates to connect toggle switches from with my circuit. So go to invert and connect and take two gates. Fine. Okay, now I'm going to edit my inputs name as A0 and A1, and also I I'm going to edit my outputs name as D0, D1, D2, D3. Okay, let's do it. Okay, now I'm going to add LED as my outputs. So I go to input and outputs and I take LED. I'm going to take 4 LED because I have 4 outputs. And I'm going to add from gates to connect my LED with my circuit. So I go to invert and connect and take from gates. I want 4 from gates. Fine. Now I change my from gates name as my outputs name. So This is D naught. This is D1, D2, and this is D3. Fine. Likewise, I change my two gates name as my inputs name. So A naught and this is A1. Okay, let's connect toggle switch with two gates and from gates with LED. Okay, let's check it. If A naught and A1 both are low, D naught will be high. If A naught high, D1 will be high. If A1 high, D2 will be high. If A naught A1 both are high, D3 will be high. So our 2 to 4 line decoder is working correctly. Okay, let's move to the next example. Okay, I am going to take adders as my next example. Let me tell you something. An adder is a digital logic circuit in electronics that is extensively used for the addition of numbers. Adders are basically classified into two types. They are half adders and full adders. The main difference between a half adder and full adder is that the full adder has three inputs and two outputs. If we assume that the first two inputs are A and B and the third input is an input carry designated as Cin. Okay, we have already seen about half adder. So let's see about full adder. Okay, hope you all know full adder takes carry from previous sum. Here I have shown you a truth table of full adder. From the truth table we can write the boolean equation for the S and C out like this. Then simplify using boolean algebra and K-map, we can get this equation for sum and carry out. Then we can construct this full adder circuit. Okay, let's build it in our seeder logic simulator. Okay, now I'm going to add XOR gate. So I go to basic gates and select two input XOR gate. Okay. I want two XOR gate. Okay, now I'm going to add AND gates. So select AND gates and I want two AND gates. Okay, now I'm going to add OR gate. So I take two inputs OR gate. Okay, now I'm going to add inputs by using from gates. So I go to input and connect and take from gates. It's a full adder, so I want three inputs. So I take three from gates. Okay. Now let's add our outputs by using two gates. So I take two gates for our outputs. Okay, let's construct this full adder by using wires. Okay, fine. Now I'm going to edit my inputs and outputs name. So let's double click. I edit it as A and edit it as B and it is Cin. Okay, I edit it as S means sum. So S, I edit it as C out because carry out. So C out. Fine. Now I'm going to take toggle switches as my inputs. So go to inputs and outputs and take toggle switches. I have 3 inputs, so I take 3 toggle switch. Then I take 2 gates to connect my toggle switches with my circuit. So I go to invert and connect and take 2 gates. Okay, I want 2 gates. As usual, I have to change its name. So it's A, it's B, and it's C in. Fine. Then I'm going to take LED as my outputs. So I go to inputs and outputs and I take LEDs. Okay, I want 2 LEDs because I have 2 outputs. Then I'm going to take from gates to connect my LED with my circuits. So go to inverts and connect and take from gates. Okay, from gates. I want 2 from gates. Then as usual I have to change its name. It's S and it's C out. Fine. Now let's connect all. Okay, let's check it. If all inputs are low, both outputs will be low. If any inputs only high, uh, the sum will be high. Sum means S. If B is high, so S will be high. If C is high, S will be high. So sum will be high. Then if any both inputs are high, then C out will be high. A and B are high, then C out will be high. If B and C in are high, and C out will be high. If A and C in are high, C out will be high. If all inputs are high, both outputs will be high, which means sum and carry out will be high. So our full ladder is working correctly. Okay, let's move to the next example. Okay, I'm going to take subtractor as my next example. You all know a full subtractor is a combinational circuit that performs subtraction of 2 bits. One is minuend and other is subtracand, taking into account barrow of the previous adjacent lower minuend bit. This circuit has 3 inputs and 2 outputs. Here, the 3 inputs A, B, B in denote the minuend, subtractant, and the previous barrow respectively. The 2 outputs D and B out represent the difference and output barrow respectively. Okay, from the truth table, we can draw our circuit like this. Okay, let's try it in our Cedar Logic simulator. Okay, let's add gates what we want. So I go to basic gates and I select AND gates. We want 2 AND gates. So I select 2 AND gates, click, drag and drop. and we want two XOR gates. Select two input XOR gates. Select, drag, drop, and one OR gate. So select two input OR gates. And also we want two NOT gates. So I select, I go to invert and connect and select a small inverter as my NOT gate. I select two inverter because I want two NOT gates. Okay. Now I'm going to add inputs. I take from gates as my inputs. I take three from gates because full subtractor has three inputs. So I take three from gates. And I'm going to add two gates as my outputs. So I take two gates because full subtractor has two outputs. Okay, now let's construct our circuit by using wires. Okay, let's do it. Okay, now let's edit our inputs and outputs name. So I edit it as B in, okay. Edit it as A, edit it as B. I edit it as D, means difference. I edit it as B out, means arrow out. B out. Okay. As usual, I'm going to add toggle switches as my inputs and LED as my outputs. So I go to inputs and outputs and take toggle switches. I want three toggle switches. So I take three toggle switch. And I want two LEDs because I have two outputs. Okay. Now I'm going to take from gates and two gates to connect my LEDs and toggle switch with my circuits. So I take three two gates and I take uh, two from gates. Okay. Uh, Now I'm going to edit my two gates and from gates uh, names as my inputs and outputs name. So it's B in, it's A, and it's B. Likewise, it's D, it's B out. Okay, let's connect it. Fine. Now our subtractor is ready. So let's check it. I'm going to check it by using our truth table. Okay, let's check it randomly. If B is high, D and B out will be high. Okay, let's check it. If B is high, D and B out will be high. Okay. If all inputs are high, D and B out will be high. Okay. If all inputs are high, D and B out will be high. Okay. If um, A is high, uh, D only will be high. Okay. Let's check it. If A is high, D only will be high. Um, if B is high, D and B out will be high. If B is high, D and B out will be high. Okay, so our subtractor is working correctly. Okay, let's move to the next example. I'm going to check it by using our truth table. Okay, let's check it randomly. If B is high, D and B out will be high. Okay, let's check it. If B is high, D and B out will be high. Okay. If all inputs are high, D and B out will be high. Okay. If all inputs are high, D and B out will be high. Okay. If um, A is high, uh, D only will be high. Okay. Let's check it. If A is high, D only will be high. If B and B in are high, B out will be high. So if B and B in a high, B out will be high. So our subtractor is working correctly. Okay, let's move to the next example. I am going to take multiplier as my next example. We all know we need 4 AND gates and 2 half adders to design the combinational circuit for the multiplier. We already seen about half adder, so it's a one half adder, it's another half adder. Okay, the AND gates will perform the multiplication and the half adders will add the partial product terms. We use a multiplier in several digital signal processing applications. We use it design calculators, mobiles, processors, and digital image processors, etc. We can construct multiplier like this from this truth table. So let's try it on our CEDA logic simulator. First, I am going to add 4 AND gates. So I select 4 AND gates. 1, 2. Then I am going to add 2 half adders. Half adders contains 1 AND gates and XOR gates. So I want 2 AND gates and 2 XOR gates because multiplier has 2 half adders. So I select one AND head and okay. Now, as usual, we add inputs as from gates and uh, so I want 2 AND gates and 2 XOR gates because multiplier has 2 half adders. So I select one AND head and okay. Now, as usual, add inputs and outputs by using two gates and from gates. So I go to inverts and connect and select from gates. Multiplier has 4 inputs here, so I want 4 from gates. And it has 4 outputs also, so I select 4 two gates as my outputs. Okay, now let's construct our multiplier by using wires. Okay, now let's edit our inputs and outputs name. I edit it as A note and edit it as A1. Sorry, I edit it as A1 and I edit it as B note and it's B1. And also I edit my outputs as C1, sorry, C note, C1, C2, and C3. Okay, fine. Now I'm going to add toggle switches as my inputs. So I go to input and output and I take toggle switches. I want 4 toggle switches because this multiplier has 4 inputs. So now I want to make connection between my toggle switches and my circuit. So I take 2 gates to make connection. I want 4 2 gates. Okay. Now I edit 2 gates name as my inputs name. So it's A naught, it's A1, it's B naught, and it's B1. Fine. Now let's connect it. Okay. Now I'm going to add 4-bit LED as my output. So I go to input and output and I take 4-bit LED display. Okay. Uh, then I want to make connection between LED display and my circuit. So I take from gates. So I go to inverts and connect and I take from gate. I want 4 from gates. 2, 3, 4. Okay. Now I'm going to edit my from gates name as my output's name. So this is C3, this is C2, edit as C1, and it's C0. Okay, fine. Now let's connect it. Okay. Now I'm going to check it. So I make A not low and A1 is high, which means 2. Likewise, B not low and B1 is high, which means it's also 2. So 2 into 2, our outputs will be 4. Okay. I'm going to make A naught and A1 both are high, which means 3, and B naught low, B1 high, which means 2. So 3 into 2, 6. So our LED display shows 6 correctly. I'm going to make A naught A1 high and B naught B1 high. It's 3 and also it's 3. So 3 into 3, 9. Our LED display shows 9s correctly. So our multiplier is working correctly. Okay, let's move to the next example. I am going to take multiplexer as my next example. Okay, multiplexer means many into one. A multiplexer is a circuit used to select and route any one of the several input signals to a single output. And single example of a non-electronic circuit of a multiplexer is a single-pole multi-position switch. When we see its applications, it's used in communication systems, telephone networks, computer memory, transmission from the computer system of a satellite, and etc. Here I have taken a 4 to 1 multiplexer. So without further delay, let's try it on our serial logic simulator. Okay, I'm going to construct multiplexer by using NAND gates. So I select NAND gates. So go to basic gates and select two inputs NAND gates. And I want 4 3 inputs NAND gates. So I select 3 inputs NAND gate 4. And I want one 4 input NAND gate. So I select 4 input NAND gates. Fine. Now I am going to add inputs and outputs by using two gates and from gates. So I go to invert and connect, and I select from gates and two gates. I want 6 from gates because I have 6 inputs. Okay. Uh, Likewise, I add two gates as my outputs. So I take two gates. Okay, fine. Now let's construct this multiplexer by using wires. Okay, let's do it. Okay, now I'm going to edit my inputs and outputs name. So I edit it as A, it's B, it's C, and I edit it as D. And also it's a small a, sorry, small B, and it's small a. These are selectors, and my output name is uh, Q. Okay, fine. Now I'm going to add toggle switches as my inputs. So I go to input and output, and I select toggle switches. I want 6 toggle switches. So I select. Okay. Now I'm going to make connection between my toggle switches and my circuit by using two gates. So I select two gates. So I go to invert and connect and select two gates. Okay. Now I have to edit its name as my input's name. So it's A, B, it's C, it's D, and it's small b, it's small a. Okay, let's connect them. Okay, fine. Now I'm going to add LED as my output. So go to input and output and select LED. And I take from gates to make connection between my LED and my circuits. So I go to invert and connect and take from gate. Okay, I have to edit its name as my output's name, capital Q. Okay, let's connect it. Fine. Now I'm going to check it by using multiplexers truth table. Okay. If select A and B are low and input A is high, the output will be high. Okay, let's check it. Okay. If select A is high and input B is high, output will be high. So let's check it. Input B is high and select A is high, output will be high. Okay. If select A and B are high and input D is high, output will be high. Okay, let's check it. Select A and B are high and input D is high, output will be high. So our multiplier is working correctly. Okay, let's move to the next example. We have just seen about multiplexer. Now let's see about demultiplexer. You know, demultiplexer means one to many. A demultiplexer is a circuit with one input and many output. By applying control signal, we can steer any input to the output. There are a few types of demultiplexers. They are 1 to 2, 1 to 4, 1 to 8 and 1 to 16 demultiplexers. Here you can see I have taken a 1 to 4 demultiplexer. So without further delay, let's construct it on our Seeder Logic simulator. Okay. Okay, first of all, I'm going to add AND gates. So I go to basic gates and I select 3 input AND gates. I want 4 AND gates because I'm going to construct 1 to 4 demultiplexer. So I select 4 3 input AND gates. Okay, and I want 2 NOT gates. So I go to invert and connect and I select CMOS inverter as my NOT gate. Okay. Now I'm going to add inputs and outputs by using from gates and to gates. So I select from gates and to gates. Okay. We all know these gates are used to connect our inputs with this circuit. Okay, fine. Now let's construct our demultiplexer by using wires. Okay, let's do it. Okay, now I'm going to edit my inputs and outputs names. So I edit it as A, it's B, I edit it as C, and it's D. Okay, likewise it's small a and it's small b. Okay, I leave it is at default capital F. Okay, okay. Now I'm going to add toggle switches as my input. So I go to input and output and I select toggle switches. Now I'm going to take two gates to make connection between my toggle switches and my circuit. So I go to invert and connect and I select two gates. Fine. Now let's edit its name as my input names. Small a, it's small b, and it's capital F. Fine. Now let's connect them. Okay, fine. Now I'm going to take LED as my output. So I go to input and output and I take LEDs. And also I'm going to take from gates to make connection between my LEDs and my circuit. So I go to invert and connect and I select from gates. Now I have to edit its name as my output's name. So double click it and I edit it as capital A, it's capital B, it's capital C, and it's capital D. Now let's connect them. Fine. Now let's check it. Okay, when data input F is high and both A and B are low, A will be high. When F is high and A is high, B will be high. When F is high and B is high, C will be high. When F is high, both A and B are high, D will be high. So our demultiplexer is working correctly. Okay, let's move to the next example. I am going to take register as my next example. Let me tell you something about register. Okay, we all know flip-flop is 1-bit memory cell. To increase the storage capacity, we have to use group of flip-flops. This group of flip-flops is known as register. Then n-bit register consists of n number of flip-flops and is capable of storing n-bit words. Let's see the classification of registers. We can classify register depending on input and output and depending on application. In depending on input and output, there are 4 types. They are SISO, which means sequential input, sequential outputs. SIPO, sequential input. Uh, I am going to take register as my next example. Let me tell you something about register. Okay, we all know flip-flop is 1-bit memory cell. To increase the storage capacity, we have to use group of flip-flops. This group of flip-flops is known as register. Then n-bit register consists of n number of flip-flops and is capable of storing n-bit words. Let's see the classification of registers. We can classify register depending on input and output and depending on application. In depending on input and output, there are 4 types. They are SISO, which means serial input, serial output. SIPO, which means serial input, parallel output. PISO, which means parallel input, serial output. PIPO, which means parallel input, parallel output. And also, we can classify registers as shift registers and memory registers depending on application. Here, I am going to take shift registers as my next example. We all know shift registers like counters are a form of sequential logic. Okay, here I have taken a SIPO, which means serial input parallel output shift registers. So, without further delay, let's construct it on our pseudo logic simulator. Okay, first of all, I am going to add D flip flops. So, I go to flip flops and I select D flip flops. Okay, I want 4 D flip flops, so I select 4 D flip flops. Okay, now I am going to add inputs and outputs by using 2 gates and from gates. So I go to input and connect and take from gates and 2 gates. Okay, now let's construct these shift registers. Okay, now I'm going to edit my inputs and outputs names. It's serial inputs, so I name it as SIN, and it's clock, so I edit its name as CLK, and I edit it as QA, and it's QB. I edit it as QC, and it's QD. Fine. Now I'm going to add inputs and outputs. So I go to input and output and I take toggle switch to my uh, serial inputs and I take single pulse generator for my clock. Okay. Now I take LEDs as my output. I want the 4 LED. Okay. Now I'm going to take from gates and two gates to make connection between my inputs and outputs and my circuits. So I go to invert and connect and I take two gates. I want two gates and I take from gates. Okay, fine. Now I have to change my two gates and from gates names as my inputs and outputs names. So let's do it. Okay, now let's connect it. Okay, let's check it. Let us take the binary information 1010 from the LSB to MSB serially at the input. Okay, so let me give my first serial input 1 and then I am going to pass on my first clock pulse. Okay, then I am going to give my second serial input 0. So then I give my second clock pulse. Then I am going to give my third serial input 1 and then I give my third clock pulse. Now let me give my fourth serial input and I pass my fourth clock pulse. Okay. Here at the fourth clock pulse we have gotten our parallel outputs 1 0 1 0. So our serial input parallel output shift register is working correctly. Okay, now let's see a summary of today's presentation. First, we have seen about logic gate simulator tools. Then, we saw serial logic simulator and its installation. After that, I explained you how to use serial logic simulator. Then, we've done lots of example under the combinational logic circuit and sequential logic circuit by using serial logic simulator. Okay, hope now you have gotten a clear idea about serial logic simulator and you can able to construct circuit yourself by using serial logic simulator. Okay, thanks for watching this video.